Let's look at how we can predict the outcome of a proton transfer reaction. And so just as a reminder, we have an acid and some base, which will react with each other, and it will make the conjugate acid and conjugate base. Now we will use these to predict which direction a reaction will go. So reactions always go from strong to weak when they're a proton transfer reaction. So whichever side the stronger compound is on, or the stronger acid, it will tend to go towards the direction of the weaker one to form that. So let's look at a few examples of this in action. So I have acetic acid here. And I have methylamine. And this will react with the proton here. And deprotonate this acid. So now we have the acetate ion. And we have methyl ammonium. Now, to predict these reactions, we'll look at the pKa of each of these acids. And we can estimate that this is about 4 to 5 based on the previous video. And we can estimate that this is around 9 to 10, somewhere in there. But there's plenty of charts that include pKa values, so you can look up a more accurate number. So remember that a lower number in pKa means it's a stronger acid. So since 4.75 is lower than 10.63, this reaction will go forward. It's close to 6 units apart. Which, because this is a logarithmic scale, translates into around 10 to the 6th. It's a little bit less, but it's close. So we'll have 10 to the 6 times more product than starting material, which is around 1 million times. So not only can we predict the outcome of the reactions, but we can estimate approximately how much more product would we have at equilibrium than reactants. And so effectively this reaction goes forward because there's be very little of the starting material remaining at equilibrium. So let's look at another reaction. So here we have a terminal alkyne, and I'm going to use a hydride. For example, you can use sodium hydride. This is a solid, and when we combine these two together, there's an H negative, and then we will make the deprotonated, because this goes over like that. So now we have our deprotonated alkyne. And then we'll also make hydrogen, which will be a gas at normal laboratory temperatures. The pKa for terminal alkynes is around 25, and the pKa for hydrogen is around 35. So this is a much worse acid than this is. It's a factor of 10 to the 10, right? Because this is 10 units apart. So this is very product favored. This reaction will go quite quickly forward. Also, if you remember about Le Chatelier's principle, where if we are removing a product out, it will tend to drive the reaction forward. We don't really need that to happen in this case because our terminal alkyne is a much better acid than H2. But if our other competition for acid is leaving the container by bubbling out as a gas, then that just drives the reaction so much more towards the products. Again, not really a necessary thing for that to leave, just because the difference between these two is so great. But it does make it completely irreversible. Now let's look at one more example. So in this case, we're looking at an alpha hydrogen from a ketone. So those are hydrogens that are on the carbon that's next to this carbon double bonded to an oxygen. And let's add in an alkoxide base. So this is T-butoxide, because there's a T-butyl group on there. So this is one of the stronger alkoxide bases. So this will remove that proton and transfer electrons over onto this carbon. So now we have a negative charge next to the carbonyl. And then we will make the protonated version, so the T-butyl alcohol. Now the pKa for an alpha hydrogen on a single ketone is around 20. And the pKa for this particular alcohol is 19. So this is actually the stronger acid. So this reaction is reactant favored. So there will be more reactants than products existing at equilibrium for this reaction. And since it's about a power of 10 apart, we would expect about 90% or so of the reaction to be in the reactant form and about 10% to be in the product form. Somewhere around in there. You might say that this is not the best. We want our reactions to go towards products, but sometimes we actually purposely choose a situation like this. And that could be so that we can control what's happening a little bit more in the reaction. We can, well, one, this slows down the reactions, and it can actually change the selectivity for where we could deprotonate. Now, on this molecule, both sides of this ketone are the same, but if they were different and we could determine that one side would be easier for the proton to be abstracted, then it would preferentially choose that side versus the other side. And we may want that to happen. And we can examine that at another time. But just know that sometimes we do like our reactions to be reactant favored, and it's not because we don't want product, it's because we want a particular product. And then we'll choose other reaction conditions to help force the reaction along. So, this has been a video on how to predict the proton transfer reactions. Remember that the reactions go from strong to weak, and remember that the pKa scale is a little bit reversed. So a lower number indicates that it's a stronger acid, and a higher number indicates that it's weaker. And so reactions like to go from lower numbers of pKa's to higher pKa's, and then that is the predicted direction of the reactions. So thank you for joining me, and we'll see you in the next video.